So they can hear us?
Yeah.
Oh, thank you. Okay. So Tharindu joined us almost 4 years ago for his PhD. PhD, he has worked on a number of things. Finally settled to this carbon aware. He was very much fixated by carbon awareness in resource management. A little bit about supporting application that requires low latency services. So, but in the process, he also developed Cloud SIM Express, which we call as a high-level environment for quickly putting together the model of cloud simulation and the task. Then from there, you can do some research on resource management. Then, of course, he also did quite a bit on practical work in managing multi-core cores within a multi-core. Then try to select some green energy so that carbon footprint can be reduced. So that is the work. So he has done a couple of publications in the process. Okay, so today is going to tell us about what all he has done during the last 4 years and prepare for this submission next month. Correct?
Yes.
Yeah, okay. Then please go ahead. Yeah. So you can sit down in the chair. Proper chair is there for you. You can sit down out there. Or you want to sit down away? Okay, you sit down here or sit down here.
Me or him?
Okay, brought stool up.
Yeah.
Okay. All right. So, hi everyone. Thank you for attending my completion seminar. So I'm Tharindu. I'm from the Cube Clouds Lab. So my supervisors are here too. So Professor Raj is my principal supervisor, and Dr. Maria is my co-supervisor, and Dr. Shashikant is my external academic. So he should be joining us soon. And all of my supervisors are here too. And Dr. Adele kindly agreed us to participate as the external academic person. So thanks very much for that. I'm really excited to have you all here. It was quite a bit of lengthier journey, so I'm really happy to share that with all of you. Let me move ahead. So for the past 4 years, I've been working on the latency sensitive applications, the problem of achieving carbon efficiency for those applications in the cloud settings. So you may have heard of some of these names. So Industry 4.0, Internet of Things, as well as these systems called generative AI. We have heard about ChatGPT. So these services runs on the cloud, and they have created a huge business value in this industry. So you can see that by seeing just the mere numbers of cloud providers have been putting into this industry. So it goes several years before as well as forecasted for the future as well. You can see that numbers are growing. So so that creates a huge business value. But then again, there are some big problems associated with such a rapid growth of the infrastructure. So one of the prominent challenges in this kind of a growth is the carbon footprint, how to make sustainable growth of the infrastructure. So even right now, cloud data centers accounts for about 1% of the carbon emissions. It's not just for the data center, but for the globally. So that's a significant number. But in reality, the actual numbers could be much higher than that. So this is one study done for the cloud providers. You can see for all major providers like Amazon, Google, and the Microsoft, the actual emission values that they have is quite higher than the value that they have disclosed. And even for the past several years, this number has been keep on rising. So there's a significant impact. And there are some certain governing bodies in terms of the carbon emission, such as the UNFC Paris Agreement. So they have outlined that data centers have to reduce their carbon emissions by at least half when we get to 2030, right? So which means for the cloud platforms, we need to have solutions to reduce this in the near term. So to understand how we can do it in the near term, it's important us that we take a look at what are the carbon emissions being made in the cloud. So we refer to one of the detailed analysis made by Google. In this month, actually, they published the paper. So in that, they outlined 2 different categories. There are operational emissions being made in the cloud, as well as there are embodied emissions being made in the cloud. So operational means the emissions made as data centers actually operates. So in that, there are two scopes. The one that we can solve in the near term is the scope number 2, which are the emissions being made through the electricity consumption. How can we reduce that? We can integrate renewables into that. And in terms of the embodied carbon efficiency, so these are the emissions being made by associated business processes, such as the data center construction, hardware transportation. So even to make those processes efficient, that might take longer periods of time due to multiple stakeholders involved. So in the near term, what we can do as a provider is to achieve efficient management of the data center hardware. So the facts covered in the blue color are the aspects that we are going to deep dive in this thesis. So the actual motivations for my PhD thesis draws from this diagram. So I spent quite a lot of time to put my thesis into one single diagram, and this is what I could came up with. So as you can see, for the latency sensitive applications, there are some performance and resources constrained environments involved. For the traditional hyperscale clouds, usually you can use that for sort of batch analytics to deliver centralized hyperscale computing. When we move to the latency sensitive side of it, you can see there are strict latency service level objectives, as well as you can see there are quite a lot of hardware heterogeneity in these environments. So two examples, IoT microclouds that we see today, they live on the co-location data center providers, which means you are leasing the infrastructure from somebody else. And that means you have very limited control over your hardware. And for the real-time cloud systems, these systems serve critical services, so which means you have bounded latency, which means you have quite a limited opportunities in controlling the workload performance. So that's the landscape we have today. And the green color you see over here, these are the existing techniques of traditional clouds, how they can achieve carbon efficiency. So things like workload suspend resume, workload throttling, as well as embodied emission things, hardware repurposing, extended use. So the opportunities to do those things in the other environment is quite limited. So in that sense, the primary challenges that we identify is that I've listed a few. So in these environments, we have tight latency service level objectives, which stops the provider from doing what we call a data center load matching, which means reduce your energy consumption when the energy grid carbon efficiency is lower. So you have limited opportunities in doing so because of the latency SL loss. And you have tight response time bounds, which means you have limited opportunities in doing multi-region renewable harvesting. And in terms of the embodied carbon aspect, you have asymmetric hardware life cycles, which limits expansion of the hardware. And finally, you can see in often many cases, there are high performance hardware profiles involved in these real-time systems, as well as many other latency sensitive environments. So that can degrade the hardware longevity, and they may lead to frequent replacements. So that is another challenge. So combining all of these things, the objective of this thesis is to propose efficient resource management approaches to achieve carbon efficiency encompassing both operational and the embodied aspects. So how can we do that? So in doing so, we have identified, over the past several years, we have identified important research questions that must be addressed. So in each of these questions, we focus on prominent cloud, latency sensitive cloud environment, and then we see how we can improve the efficiency in those environments. For the first one, we take a look at the IoT microclouds. And for the second one, we take a look at real-time cloud systems. For the third one, we take a look at the application performance management in multi-region harvesting. And for the fourth one, we take our look at the embodied carbon aspect, which is the in the inference clusters. We will talk a little deep about these things in the coming slides. And in addressing those research questions, we contribute through this thesis. The first one is we contribute a taxonomy and detailed literature analysis using the taxonomy. And in there, we identify the research gaps. So using those ones, as well as the research questions, we propose a dynamic power budget for the microclouds to address the Q1. We propose a framework for the real-time clouds to address Q2. We propose a load shifting technique for the low latency applications to address the Q3. And we finally propose an aging-aware core management technique to address the Q4. So that brings us to the first phase of the seminar, which is about the introduction part. And in the next section, we will dig a little bit deeper into each of these research questions. And we talk about what is the problem that will be addressed and what was the limiting factors in the existing approaches and how did we solve that. So moving forward, we will take a look at the first project that we involved. So it's majority of the work comes from one of our paper published in 2023. In this specific project, we take a look at the emerging IoT microclouds. So if you are not familiar with that, so IoT means Internet of Things, which are the applications that require low latency. Because of that, they need to be deployed at the edge of the network. So cloud providers deploy what we call a microcloud, which is a lightweight data center that will be deployed all around the world, like in different geographical locations. So like if you think about it, if you want to build data centers, many places around the world, that's going to be costly. So the efficient approach to do that is to rent the resources from someone else. So cloud providers get them from what we call a co-location data center provider, which means providers build data centers for multiple tenants. But the problem associated with that is these data centers are built in urban areas closer to the users, which means they draw power from the congested power grids. So if you want to scale up as a co-location provider, you have limited power capacity. So because of that, what those guys do is they impose what we call the soft power budget to each of the tenant and then oversubscribe their capacity. But as an adverse effect of that, what the microcloud has to do is they have to control their workload performance to accommodate with the power budget, right? So our solution or our approach to this problem is to integrate renewables, which are easy to provision. We do that on-site by on-site renewables. But the problem with that is renewables has their own supply dynamics. And when you have multiple microclouds around the world, the supply dynamics changes. So the objective of this problem is to relax these power budgets efficiently while optimizing for the application performance. So let's take a look at what are the limitations of the existing approaches in this problem. So usually these clouds connect through wide area networks and they have congested traffic performance. So existing approaches, they usually do not focus on that one, as well as they don't really do fine-grained power optimizations, which is what we are going to do in our work. So in our solution, first we propose what we call a dynamic power budget to relax the power budget constraints. And then we propose a decentralized task scheduling algorithm to utilize that power budget across the regions. This is a high-level system model image of what we are going to improve. So like I said, there are multiple microclouds. In each of the microcloud, you have on-site renewable energy, and each of the microcloud has a local scheduler which manages the task execution. And what we propose here, the first one, dynamic power budget. So when we took a deeper look at the power delivery infrastructure of a microcloud, this comes from a co-location data center provider. Each of these are the tenants. So this is our microcloud. So there's a thing called power delivery unit, which delivers the power. And because of the soft power budget, what the cloud provider does is it limits the power to a certain level that the cloud can operate, which means each PDU is now underutilized. So we take that as an opportunity, we provision renewable energy for that capacity, and combining both of these things, we now have a dynamic power budget. So that's our proposal for the on-site. And then across the sites, we propose a decentralized task scheduling algorithm, which operates in two phases. So each of the microcloud take a look at their power consumption against this dynamic power budget, and then they will determine when to offload some of its tasks if the power demand goes beyond the budget. So they do that by these steps, and how they do it, they broadcast a request to all the other nodes, and nodes reply with information, and they determine which one to deploy using a lexicographic method, and then they schedule the dispatch for the tasks. So to evaluate our technique, we use state-of-the-art scheduling algorithms as well as real-world traces. We use extended CloudSim toolkit in this scenario. So in this simulated environment, what we found is both baselines that we used, they failed to handle the WAN traffic congestion. So latency increases as the congestion increases. But only the other approach that we found is that they are able to optimize when that goes on. So in the big picture, we found that we get 19% power overdraw impact reduced and 47 and 49% task performance impact improved. So that's what we bought with our first project. And the limitation of this project is that we use statistic models for the prediction. So there are two prediction tasks in our work. So both can be benefit using ML-based models. And since we use the simulated environment, it may not capture fully real-world variations. So that brings us to the end of the first part. We can, if you have questions, please free to raise them, or maybe we can discuss in the end as well. So I'll move on to the second one. So in this work, we take a deep look at what we call an environment which has really tight performance constraints. So we work on real-time clouds here, and the work comes from one of the paper that we are in the process of publishing at the moment. So in real-time clouds, the major performance constraint with the real-time clouds is that they need an infrastructure which deliver deterministic performance, which means you can't really handle unpredictability in your infrastructure, because if that happens, application may violate their latency boundaries. So what we found is that you need that deterministic nature, but then again, these systems internally, they provide what we call component level fault tolerance, because on the infrastructures, there could be unforeseen situations where the component fails, so you need to recover from that. So that's what we see in the existing systems. So what we want to do is we want to integrate renewable energy to improve its carbon efficiency, but the renewable energy has supply dynamics again, so that challenges the power stability. Our objective is do the integration, but do not compromise the deterministic application execution. So how did we do that? We found that with the limit existing approaches, there are two major solutions. The first one is called vertical scaling, which introduces resource contention, degrades the performance of the application. And the second one is hardware throttling, which introduces slower performances, again, not good for the performance of real-time systems. So in our work, we propose two-fold solution for that. First, we propose what we call a VM execution model to exploit the component level fault tolerance. And then to utilize this model across the servers, we proposed a packing algorithm. And then we practically implemented the system with the OpenStack, and we evaluated the system both practically and using the simulations. And then we finally open sourced our implementation. So this is a high-level look at our system. Each of the server integrates renewable plus grid mixes. And on the application layer, this comes from specific application, they supports the fault tolerance. Let's say one of the VMs had to be evicted, then the real-time system will be able to recover from that. So that is our system at the moment. Now I'll explain how we implement our solution. So these are like three-step solution that we have here. The first one is execution model. What we first did was we went to the CPU of the real-time server and we implemented what we call a renewable-driven cause, which means dynamically we pick a set of cores that will be active in a given time, and the remaining sets of cores will be put in a low power profile, which will effectively bring down the server power draw. And we change that according to the renewable energy availability. So building on that, we used our execution model, which guarantees that each of the VM, if it's alive, they will be pinned to these cores. If the cores are not sufficient, then we will evict those VMs. So that will be recovered back from the application layer. So that's the idea of the execution model. And we then notice that in these systems, when you're operating at scale, for the VM packing problem, you need to have quite an efficient algorithm to pack the VM as soon as possible. But when you implemented such fine-grained CPU management policy, then these two layers need to communicate. That might take more time. So in reducing the time in that, we proposed a new concept called green cause concept. What that does is it takes a look at the power domain characteristics and convert that into the resource management software layer. Each of the node in the system calculates this and give that information to the control layer of the infrastructure, which does the packing. So based on that, the control layer is able to now plot each of the server into a two-dimensional space of the eviction probability and renewable energy harvesting possibilities. So to efficiently utilize this model, we proposed a packing algorithm which does the optimization. It has a lower complexity, so we can achieve faster packing decisions. So this is our implementation. So what we did was we first implemented an on-node service to achieve the renewable driven cores. We use per core C-test feature of the Intel processors, which is supported by the AMDs as well, many other vendors. So we just need to change the implementation per the vendor. In our test bed, we used Intel cores. So we implemented a daemon service runs on each of the host for that. And then we integrated that with the OpenStack's on-node compute service by modifying the existing resource management software layer. So we synced it with the sleep management, and then we enabled the dynamic CPU hot plugging, which means if you take off certain set of CPU cores, Nova Compute has to know about it. Otherwise, their state will be changed. So we fixed that, and then we implemented a few features to support the whole system. Then at the control layer, we implemented a new controller to control this sleep management flexibility, so that if we provide an energy signal, which is on number 1 over here, the controller is able to sleep and then wake up cores according to that. So for the packing algorithm, we implemented that using existing CPU layer class in the OpenStack control plane. So this implementation you can find on GitHub. It's available for the public use. And this is how we did the performance evaluation. We had a practical and a simulation test bed. We used real world traces that's collected on the public cloud providers, as well as practical real-time applications that has been part of Linux Foundation projects. So we used state-of-the-art comparing techniques, and I'll show you how our system performed. So we first evaluate the application impact in doing our technique. So what we see over here is that if we use this state-of-the-art technique which uses resource contention, you can see that when we change the renewable energy, which means the power capacity somewhere around here, you will be, as an application, experiencing a spike in its mean latency for the real-time system. So this was calculated inside each of the VM using a different tool. And you can see that for the Harvest VM approach, which is the state-of-the-art, you have the spike. And a deeper look at that, how that works for the Harvest VM, you can see when you change the number of cores, which introduces resource contention, and that impacts the latency. But with our system, we compromise at one point, which is we will have a slight interruption to the application execution, but we tolerate, because of the RT system tolerates the fault tolerance, it will be able to recover the system back and then restore system performance. So from this point onwards, the application will have the same performance. So that's the benefit in our system. We observed, and we can see that there's a 6.52% times reduction in the latency variance. So that's one aspect. And finally, for the it's good that we maintain application performance, but the whole point of this thing is to have the renewable utilization. And for that, we used large simulation test bed at scale. So we will see that our system is able to reduce the application impact as well as harvest the renewable energy at the same time, comparing to the state-of-the-art techniques. So finally, the limitations of our system is that there will be some scheduling overhead associated with our implementation. Also, we rely on the backup power for the energy transition, and our system may require the real-time system to efficiently handle the fault tolerance. And the one before the last one, in this work, what we did was we took a deeper look at the low latency applications in quite popular multi-region renewable harvesting mechanisms we see today. This also comes from one of our work in paper that is in progress for the submission. So in this work, we know that in most of the clouds, what they do with the renewable energy harvesting is that they do cross-region load shifting, which is move your workload from one place to another depending on the energy availability. So in that case, we notice that low latency applications usually is omitted, because when you move from one place to another, there will be latency violations. So what are the solutions to do that? You can do what we call a local retention, which means you have a mix of applications. You keep the low latency applications locally as much as possible and offload the remaining applications. So that's one way of looking at this problem. but that is challenged because of the renewable supply values, which is you have lower capacity, which means you have lower compute resources, which means eventually you will have to offload your applications. So in our problem, we try to efficiently manage low latency applications during this compute resource shrinking problem. So the gaps in the existing ones is that existing ones may use CPU throttling, which degrades the performance. And also they do not consider this local retention aspect. In contrast, we use what we call simultaneous multi-threading feature of the CPU to create a static set of resources. And then we use a load shifting technique to utilize that across the regions. So this is a high-level idea of our solution. We have two different server pools here. Each of the server has the same number of physical cores, and using the same core deep idle technique we used in the previous work, we implement the renewable supply dynamics over here. Since we have simultaneous multi-threading enabled in one of the servers, what it basically does is it doubles the available logical cores in the system. So this is what the application sees. So if you just take a look at from that part, you can see it depends on the renewable energy availability. Whether you have a peak, whether you have a valley, you will have, let's say, four physical cores or maybe logical cores across the pools, right? It changes back and forth depending on the supply value or the peak. And our scheduling algorithm, what it does is it efficiently manages the VMs between low latency as well as best effort ones, depending on the number of cores. So if the compute resources goes to the other pool, that's what we call the chasing from one pool to the another. If it switches back, we chase it back. So in that sense, we can retain low latency applications inside the local region and maybe offload the best effort applications across the region. So that's the idea behind our technique. We evaluated that using a practical setup with a 2-node cloud setup. And then we use real world data for that. So in comparison to the existing application flexibility based state-of-the-art technique, we can see that our technique is able to dramatically reduce the number of low latency VMs that has been offloaded. So 80% in the numbers. And also we can see in terms of end user latency, which is over to that plot, we can see there's a 43% reduction in the latency variance in our system. And the penalty of our system is that you may execute VMs on the simultaneous multi-threaded cores. And we took a deeper look at how that penalty works. So we found that if the CPU is not that congested, you will have a very minimal penalty. But if it is, at the worst case, if it's highly congested, you will have about 11.97 penalty. So that's the compromise of our system. So the limitations obviously is if you have microsecond scale applications, they may notice the SMT core performance penalty. And also we implemented a coarse gain admittance policy for the scheduling, so they may affect the performance. And finally, we have come to the final project in my PhD thesis. So this one is about the embodied carbon reduction. And it talks about quite a hot topic, which is about low latency large language model inference clusters. So this also comes from one of the papers. It's in the revision process at the moment. So the problem of this is that we all know that the cloud later LLM models have been gained significant traction now. Because of that, the providers try to scale their infrastructure to cater the rising demand. But existing studies notice that when they do that, their CPU components, such as the die, the main board, these ones accumulated most embodied carbon in the cluster. So we noticed, or we thought that if we can extend the CPU life, we can further, reduce the impact of that accumulation. But how can we do? When we try to do that, the CPU will be operating beyond its operated lifetime, which means there will be unreliability issues. And we notice the most important unreliability issue is called silicon aging. So in this problem, we try to extend CPU life to further amortize inference cluster embodied carbon. But in doing so, we'll try to manage the effect of the silicon aging. So let's move forward. And the limitations of the existing approaches. So we went past all the way up to 2008, had a look at the work that has been done for the silicon aging management. In that we found most of the techniques do not like suitable for the clouds because they require fine-grained CPU performance profiling. So that's one issue. And the other one is nobody like have focused strictly on the inference clusters for this problem. So in solving that, what we did was we made an investigation on how the CPU is used in the clusters, and we proposed an aging-aware CPU management technique to exploit on those usage patterns. So this is our system model. In each of the servers, like in modern inference cloud deployments, you have an inference cluster, you have an inference service control plane, which has a cluster level scheduler. So the request comes from the applications directed into a server, and that comes here. So we also usually know that these requests have been executed by the GPUs, but before doing that, there's a bunch of tasks that needs to be done at scale. So like request batching, queuing, loading, and the request execution. So that triggers a set of CPU tasks, and that goes through to the CPU. So we intercept in the middle, we try to optimize that process. So our model for the CPU aging, we had a look at the literature, and then we found the most prominent one comes from what we call NBTI induced CPU aging, which means over time as your CPU operates, the transistors in the CPU, they degrade slowly, and what we call for that phenomena is the degradation in the threshold voltage. So as a result of that, your operating frequency of the CPU goes down. So I have to remind that this is a slow process, happens over several years. So once that reaches a certain threshold, thus your CPU may exhibit unexpected performance issues. So we use that as the reflection of the CPU aging. But at the same time, we took a look at how the CPU is utilized in the LLM clusters. What we found is that these are the CPU utilization patterns. So you have a large number of CPU cores in each of these machines. This is a 22 machine cluster. So you can see that the CPU utilization almost often concentrate on lower number side of the CPU cores, but occasionally you may have the spikes, right? So which justifies to have a large number of cores, but then again, they are quite underutilized. So that's the usage we found. And in our solution, we are going to exploit that. We propose two independent algorithms to optimize that. The first one handles the task to core mapping, which tries to even out the aging between the cores. The second one does selective co-idling, which again uses the deep idling technique that we implemented, which tries to slow down the aging of each of the CPU cores. So in combination of that, we propose our aging-aware CPU core management. And this is the evaluation approach. So we used the simulator from the Microsoft, and then we extended that to model the CPU aging part. We also used the Azure inference traces for this one. When we compare the performance of our system to the state of the art, what we found is that with accelerated by our deep idling method, our approach is able to have the best frequency management performance out of the three, and that is reflected in the longer period of time. In the long run, we had a look at the cluster embodied carbon reduction. So the green one is our proposed technique, which is able to significantly get down the cluster yearly embodied carbon emissions. As well as in the short term, what our technique does is it can reduce the CPU underutilization patterns. You can see for the both of these tasks, the idle CPU cores close to 100%, but with our one, it concentrated down. So you can see P1 and P90 values for those ones. So that's one thing. And what I have to also emphasize is that since we are doing dynamic core idling, we may introduce CPU oversubscription. So that is the compromise in our system. So by looking at the values, we can see we achieve 37% reduction in yearly embodied carbon emission, 77% reduction in CPU underutilization. And the only compromise in our system is the inference service quality impact. We found that it's less than 10%. So finally, this is the limitation of the system. So if you have higher inference throughput, oversubscription may increase, that could impact. And also we used a simulated environment, which is high fidelity, but again, it may not capture full real world deviations. So that would be it for all the proposed solutions, which address the introduction, the problem domain we introduced over here. And finally, I would like to conclude my presentation. So this is how my PhD journey unfolded. So the introduction part that we did and the taxonomy part, this is structure. So inside here, these are our main contributions. It lists down all the things we discussed in the previous slides. So as a result of all this exploration, we have identified some suitable, exciting research directions in this domain. So it's a quite new domain, especially in the embodied carbon aspect. There's quite a lot of work to do still with the existing literature for the embodied carbon. They're working on the accurate modeling aspect. So once you have that, then you will have the resource management implementation part. So there's a lot to do in this regard. So a few things I will mention. So one thing we can do is we can do renewable powered CPU cores. Instead of having changed the number, we can physically separate those cores, and how that would benefit, it's left for the resource management layer to decide. So that's an exciting area to improve. Also, we haven't tried the thermal management part of this carbon reduction. So that's one exciting area. And also, instead of having high performance profiles for the latency sensitive, we can do sustainable performance profiles. So that's one other thing you can explore. So with that, I would like to conclude the seminar with the actual research outputs that have been made. So we have published several papers as an output of this work. So the previous ones are in the process of submission, also these ones, and then we have a couple of works that's planned for the submission. And not only that, we have open sourced software tools that we have developed throughout these years. So all of these ones are available publicly. So that is for the benefit of the research community. And finally, I would like to acknowledge the support given by my supervisors, Professor Raj, Dr. Maria, and Dr. Shashikant, as well as the Professor Uday as my committee chair, and for all the lab members who are here. So we had lots of faces when I joined first, see a lot of new faces as well. So they have supported us throughout this journey, both in the work as well as outside the work. So I'd like to acknowledge all of you for that. And my family finally for supporting me throughout this journey. And that brings us to the conclusion of this seminar. Thank you very much.
Thank you. Thank you, Tharindu, for a clear presentation of your results.